I'm starting the streaming to YouTube now. Yeah, these days it's difficult to predict how much time it takes to finish a game or even to get a game started because all games now, are multiplayer and then you have to wait for other people to join the game, and the good old days of Tetris is gone, or Pac-Man for that matter. Yeah, same here. I only play games that I can just abort, uh, otherwise known as bot games. So no one is going to complain and go like, Tech is going AFK, let's report him. Hmm. Oh, Tetris VR, that has got to be fun. Alright. Okay, so we're going to get started today. I got some stuff on my tablet already, kind of as a reminder of, what I need to talk about today. So we have three instructions that I kind of want to go through: LDI, LDST, and I also want to talk about the concept of labels. Um, okay, there we go. So that's kind of the outline of what we'll be doing today. So let's go ahead and get started. But before I start, let me just kind of let people know how to uh, copy a file or how to clone a file, because apparently not everybody knew how to do that. All right. So let's see. Where's my file? I thought I got it open somewhere. Apparently not. Okay, I don't need that. And, well, it's okay. I can just navigate to it again. Nope, it's right here. Okay. So the first thing is, how do we clone a file? So there are several ways to clone a file. If you just right-click on the file in Google Drive, you can. I'm not sure whether you guys see this or not, but you can make a copy. Um, Is that kind of what you guys did? For those of you who did make a copy of my file, did you just, kind of right click and then select make it? Yeah.
Yep.
Okay. Thank you. And you have to be careful because once you click it, you cannot create a copy within the same folder. So you're gonna have to specify a different folder where this file goes. But that's the easiest way to do it. There's another way to do it. So the other way to do it is to get into the file first, and then you go to the file menu, and then from here you can also click make a copy. What this will do, this one is slightly different, because if you do it inside the document, it will actually let you select where you want the copy to go. So you want to go to the folder and go all the way back up to your Google Drive. So you have to go all the way back to My Drive, and then from that point you can navigate to one of your subfolders. So this will create the copy of this. It will clone the file where you point it. So it gives you a little
This
bit more
one is
control.
slightly different.
Go ahead. Oh, okay. So anyway, that's how we make copies. The assembler only runs in Google Drive. Nowhere in my documentation, nowhere in my instruction said anything about running this, in Excel, or to download it or re-upload it or anything like that. Okay, so it's not going to work because it relies on a lot of formulae that are unique to Google's spreadsheet. So there's that. All right. So what we'll do today is I'm going to go explain a few instructions, and there are a few things, that you probably should have learned from the lab on Tuesday. So one of the spreadsheets that you probably will be referring to quite a bit would be opcode table. So you can make a copy. I mean, all of these documents and spreadsheets, you can make a copy and then you can annotate and add your own notes, or do whatever you want with it, right? So go ahead and make your own copy if you want to. It's not a problem with me. So what we'll do today, um, the Google Sheet. Oh, are you referring to the assembler? The assembler took a little bit of time, like several semesters. This one, which is really just for documentation purposes, is not too bad. The assembler is also constantly getting updates. In fact, if you go to the first page, it has a little revision history thing, so you can actually track down, what I have done to the assembler over time. But what we'll do today is to look at a few kind of important instructions. One is LD, which is this one. All right, so we have SSE9194 again. Trying to join the Google Meet. All right, so we have LDI, and then we have LD. Okay, so I'm just gonna remind whoever is SSE 9, I cannot remember, 9194 or 9141. You might want to change your name to your real name, because otherwise I'm not gonna let people into the Google Meet. The best way to do it is really just to sign into apps.losreels.edu first, and then join the Google Meet as a Los Reels person. Because in that case, I don't even need to let people in. I mean, you just get right into the Google Meet. So make that adjustment or change the way you sign in. Okay, so all right. So moving on. So we have LD, and then we also have the ST instruction over here. So these are the three that we're going to focus on. But as we focus on these things, we'll also be explaining how the processor works. Okay, so on Tuesday, I kind of mentioned that today we'll be talking about how the processor works, and we are going to do this edge by edge. Okay, if you guys remember those engine model thing that people still buy. Okay, so let me just kind of show you what I mean by that. Engine transparent V8 model. So you can still get these things. Apparently they're not cheap either. Wow, I did not know they are this expensive. Holy smokes. They're kind of cool. So this is basically text toy processor. Okay, you're not gonna slap text toy processor into an actual computer. I mean, even if you can turn it into silicon, it would just be a waste of money to turn it into an actual hardware processor. Just like you're not gonna run one of these things in a real car. However, if you want to learn how an engine works in a real car, this gives you a lot of it's a tool, right? I mean, it shows you the valves, it shows you the piston, it shows you the crankshaft, it shows you a lot of things that are actually in a real engine. And it does so, in a way where it doesn't go too fast, right? Because you can just turn it a little bit, and then you can see how the valve, open and which one closes, and how the piston is moving in, relative to the opening and the closing of the valves and so on. That's exactly what we're gonna do today with text toy processor. So it's gonna be an interesting lecture. All right. Yes. Yes, I tend to go all over the place, Jonathan. All right. So the first thing is you also might want to learn, especially because we don't need to do it now. Now is a good time to learn how to start the processor using the command line, because at some point it is going to be quite useful to be able to start it from the command line. So what I'll do is I'm just getting my command line ready. All right, so there we go. All right, so to do this in Windows, you kind of want to make sure that all the files are in the same folder. It makes it easier, but it doesn't have to be that way. Okay, so the way we do this is, I think I have explained this already. I think I explained this like within the first 1 or 2 weeks of this class in the semester. So this is nothing new. Okay, so Java is the command. -jar is called a switch. It tells the Java program whatever follows is a Java archive file. Okay, that's what jar stands for. Mine is located in here in my documents folder within CISP310, and name is logisim310.jar. Now, where you put your jar file is up to you. My advice is, if you don't want to mess around with file paths, relative paths, absolute paths, and stuff like that, put everything into one folder. Okay, it really just makes everything a whole lot easier. And in that case, you want to run this command after you have used the cd command, change directory to the folder where you have all the files. It's because in that case, you just have to refer to logisim310.jar without having to supply all of the entire path. Okay, so that's up to you. I don't use Ubuntu, but it's close. Aaron is close. I use Debian, which is the I'm trying to think of the word. It's at the tip of my tongue, but I just cannot. I was about to say autistic, but no, it's not autistic. It does relate to autistic, but it's not autistic. What is high function autistic people? No. Okay, when the word exactly, it's a Asperger. Yeah, this is Ubuntu's Asperger older brother. That's I think that's a really good description of Debian. How Debian relates to Ubuntu. Ubuntu is kind of the fun, outgoing younger brother of the two, and then Debian is the kind of Aspie. He's an Aspie older brother. Kind of quiet, stoic. Doesn't like to talk, but gets the job done nonetheless. So there you go. All right, so if you enter the command up to this point and press the enter key, it will start Logisim just fine. But I want to show you how to start the processor as well. So the next argument to the command line is where we find the processor file. So since I put my files kind of all over the place, so I have to supply the full path name. So once again, if you put everything within the same folder, then you don't need to supply the entire path. And remember, in Windows, you need to use \, not /. I'm not going to teach how to use Windows command line, because that I would assume people can learn that by themselves. And if that assumption turns out to be false, let me know. There we go. So now I press the enter key and Logisim starts up, and it also starts up with the processor already loaded. And you might think that this is really just a shorthand for now, and for now it is true, but later on we want to trace the code as we execute instructions in the processor. Then it becomes like super duper useful. So we'll get to that point, and I'll explain that when we get to that point. Alright, so now with the processor, I want to play with LDI first. Okay, so let's just say that LDI, well, let me think. Do I want to play with LDI, or do I want to play with the other two? Let's do LD first. Okay, so I changed my mind, and we're gonna start with the LD instruction. And my tablet has fallen asleep already. There we go. So we're gonna do an LD instruction, and LD, if you look up the opcode sheet, okay, it has a format like this. Okay, so we have. Okay, let's just go back to the opcode sheet. Okay, there we go. So with LD, which is here, you can see how it refers to X and then Y in parentheses. The parentheses is here to emphasize that Y is dereferenced. Okay, and you can also see how the documentation, column C is kind of using C syntax to try to explain, what an instruction does. And in this case, there are two. Okay, it depends on whether you want to look at memory as memory or whether you want to look at memory as an array that I call RAM. So, Either way is okay. There's no right or wrong thing here. I personally tend to look at memory as memory, so I use x equals to star y as the proper documentation of what this command does, or what this instruction does. So what y is being used? Y is being used as an address. Okay, so whatever register you use to specify y is supplying the address in RAM. And whatever is at that location in RAM is copied to whatever you specify as register X. Okay, so now we'll go ahead and make it more concrete. So we switch back to the tablet, and let's say I want register X to be register C, and I want register Y to be register A. So in other words, the actual opcode I want would represent something like this. And in reality, what it does is C would get whatever A is pointing to. Whatever register A is pointing to in RAM, the content of that location is going to be loaded. Okay, it's going to be copied to register C. That is what the instruction is going to do. So obviously I can use the assembler. Okay, after all, that's kind of the whole purpose of the assembler, is to help me so that I don't have to assemble the instructions myself. I don't have to put all the bits in together. But I think at first it's probably a good idea to practice it a few times. So now I switch back to the opcode table and see if I can put this together. So according to column A, the known or the fixed bits, the most significant 4 bits are fixed. So we have 0, 1, 1, 1 as the fixed bits. And then we have XX, to specify whatever I want to use for register X. In this case, I want X to be register C, and since we count from 0, register C is a 1, 0 in base 2. And then register Y is register A. And register A is represented by 0, 0. So now we have 0, 0 to represent the YY. And then somebody may ask, but where did you mention that? It's all at the top of the spreadsheet. XX specifies one of the 4 registers. Register A is 0, 0, B is 0, 1, C is 1, 0, D is 1, 1, and so on. All right. So now we can switch back to the tablet. Okay, so I just I just filled in, this is specifying register C, and this is specifying register A. So this is corresponding to XX, this is corresponding to YY, and because the RAM component requires us to enter the content, if you want to inject content into RAM, you have to enter that in hexadecimal. So now we have to convert this into 7, and then this into 8. So 7, 8 is going to specify the instruction that we want to execute. So now we switch to here, and then we just go to RAM. So this is one way that you can quickly enter an opcode. You just kind of don't even bother with right click and then say edit content. You can just click on it. As long as you're using the poking tool, you can just poke the RAM, a certain location in RAM. As long as it is within the small window that is being displayed, you'll be fine. So we specify 7, 8. I just literally typed 7, 8 on the keyboard, and that gets entered into this location. And then I also want the next location to be 0, 1. So here is 0, 1.
Webcam is over the.
Oh, yeah, I know. I have to move myself. Let's see, I can move myself all the way to the top because we seldom need to use that portion of the screen now. There we go. Thank you. All right. Well, I can also kind of just remove my webcam entirely. That works too. But then you guys won't be able to see me rolling my eyes, which I think is important. That's why we teach in synchronous mode, so that you guys can see me roll my eyes when, yeah.
Very interesting questions are asked.
Yes, yes. Interesting in a certain way, yes. But there are no bad questions. There are no bad questions. All right. So this is the program. Okay, so I'm not even using the assembler. Ah, okay. So this is the whole program. Okay, I don't even need to use the assembler because I want to practice, how to enter the opcode, manually, and how to figure out all the different bits, manually. So there we go. The poke tool isn't working. So you make sure that you're using the poke tool, which is what this is, and then you just click on the RAM component. So make sure you're poking at the RAM component, not double click. It's just click, just one. And make sure you're not clicking on the ROM component because you cannot overwrite the ROM content just by, well, maybe you can. Don't touch the don't touch the ROM, okay? Because we just want to change the RAM component. Okay. All right. All right. So now we need to really focus. Okay. I just want to make sure that the text channel is all kind of sort of quiet at this point because this is where I'm going to explain how the processor works. Okay. Because I explained the other day that these wires, okay, these wires flying all over the place, they're kind of like wires attached to puppets, okay? And the puppet master or the puppeteer in this case is this thing over here. Okay, this is the microcode engine. Okay, everything. I mean, it's not exactly starting at a certain place, but basically the bottom part here, from here all the way, including the ROM. Okay, including the ROM, including these things over here. That's kind of the microcode engine, which is the puppeteer. And what we know when we reset the processor is that the microcode pointer, I know it looks like U code, but U is used a lot in engineering to represent micro, which is mu. Kind of looks like a cross between a P and a U. So that's microcode. Okay, this is microcode pointer. So the microcode pointer, just like all of the other registers, it gets reset to 0 when the processor starts. And this really is the most important part, of it's basically the heartbeat of the entire processor. Okay, it directs the whole processor what is the next thing to do. And because the register has 000, then whatever is presented to the Q port is also going to be 000. Okay, so there are 12 bits here, not just 8. Okay, because I kind of overestimated how many locations I need in the ROM. So there we go. We are stuck with 16 locations per opcode. It'll be clear what I mean by that. So now ROM is always enabled because the select pin is connected to a constant of 1, so it's always enabled. And as a result, the A port specifies where we want to access, which is location 000 at this point, and it has this content of 1080007, which is in hexadecimal. Whatever this content is presented to the D port. So if you click on the D port using the poking tool, it will basically mirror the exact content at that location in ROM. So what does that mean though? Right? I mean, this D pin, it goes to a splitter, and then some of these things is split again, like microcode data is brought up here as a tunnel, and it got split up again. Okay, so for the most part, you don't really have to know exactly which bit is going where, because that's the reason why I use a whole lot of tunnels, because I can then refer to these bits, or sometimes multiple bits, using the name, which is a whole lot easier to remember than the bit 7 and 8 of after splitting is blah blah blah. Okay, so I can just refer to the name. These names is somewhat systematic. We'll see how they are systematic in just a little bit. All right, so what we are seeing right now is called the fetch cycle. Okay, so when the microcode pointer is at location 000, and we have a rising edge because the clock is 0 at this point, and when I Control T, to make it tick just once, to make it transition, it's going to have a rising edge, and this is called the fetch cycle. So you might want to write it down, okay? Take notes, okay? This is called the fetch cycle. So now we want to know, okay, why is it called a fetch cycle? What is it doing, when it is in a fetch cycle? All right, so I cannot answer the individual questions right now because I think you guys probably would be better off just following my demonstration instead of trying to do it by yourselves. It checks RAM. Well, it actually reads RAM, okay? So this is where we need to, at first, it's going to be difficult because you guys don't really know where things are and stuff like that. But we have several key components, okay? Things that really are essential to the execution of instructions. So one of these is RAM, okay? So what you need to do, when you are checking what the processor is going to do, is to check these key components first, okay, to find out are they active. So with RAM, it's pretty easy to see whether it's active or not because if the select pin is a 1, that means RAM is active, okay? And when it's active, it's usually active for a reason, okay? So unless, in an exam I want to ask a trick question, and I turn RAM on but not using it for any purpose, okay? So that's possible, but we are not in an exam right now, okay? So when RAM is on, it typically means, oh, okay, we are doing something with RAM. So when select pin is a 1, that means we are using RAM. And the next natural question is, are we reading or writing? Okay, so we need to look at the LD pin. So the LD pin right now is a 1, and that means we are reading from RAM. In other words, the D port of RAM is acting as an output, and someone else is listening to it. We don't know who's listening to it yet, but we know somebody should be listening to it. Okay. And we also know the A port is going to specify where in RAM we're going to read, okay? And we want to find out, who is specifying the address of RAM eventually, and who is reading the data port, okay? So are we doing okay so far in terms of, just kind of looking at the RAM component and figuring out whether it is in use, and if it is, what operation we are trying to do at this point? Okay. Yes, when RAM load is a 1, we are reading. So I do expect people to study. Studying means you need to gain the understanding of the mechanism of how these things work, and this is something that we talked about on, I think it's either Tuesday or last Thursday. I cannot remember which day. But you can also, always refer to the reference. You can go to library reference and go to the document for the RAM component and read that also. Okay, so there's online help. Okay, so let me pull this down a little bit so you guys can see. So there's also online help, built into Logisim. But we do need to get familiarized with all of these components because I don't want to use time in class to kind of go back to re-explain something because we are going to be pressed for time. All right, so now my next question is, now that we know we are reading RAM, the next question is, who is specifying the address? So the easiest thing to do is to make sure that you're in the poking tool mode and then click on the wire to find out, okay, where does it go? And obviously, it only goes to a multiplexer, okay, which means we're not fully answering the question yet, okay, because we're going to a multiplexer. But the multiplexer has a select pin. The select pin is always the one under the gray dot, with a multiplexer, and also a demultiplexer. And in this case, the select pin has a 1 in it, which basically means input 1 of this multiplexer connects to the output pin. We know the output pin is going to the address port of RAM. We just need to know now who is connected to input 1 of this multiplexer. This wire connects to input 1 of the multiplexer, and that goes straight out, it comes out from the PC, okay, the program counter. It comes out of the Q port of the program counter. And a register like the program counter cannot stop outputting. Okay, it's always outputting whatever its content has. So now we know the program counter is connected to the address port of RAM. Okay, the program counter is specifying where in RAM we are reading. So the next question is to ask, we know, it's outputting 7, 8, with the D port, but who's reading it? Okay, so now we need to track down all of the things that this particular node connects to, and this is why the poking tool is really useful, because it highlights the entire node. Even if things are separated by tunnels, it will still highlight. So that's really kind of handy. So so you might want to develop a particular order, when you explore things. So I would just go to this one first, because it just kind of pops up. So with this one, I'm not concerned because this is a demultiplexer, and the demultiplexer is disabled because some demultiplexers can be enabled or disabled. If a demultiplexer is disabled, then none of the output is active in any way. So we know we don't have to worry about this connection because this demultiplexer, all of the output of this demultiplexer are turned off. So we follow the wire again, and this time it goes into the this multiplexer. So now we need to track down this multiplexer and see where it is going. So this multiplexer eventually, okay, what if it is, okay, first of all, the select is specifying, input 0. So this is a dead end already. We know it is already a dead end because the wire, the node we have selected is going into input 1 of this multiplexer. But the multiplexer has the select being, saying 0. So the output of this multiplexer is not even coming from the node that we have highlighted. So we know we have hit another dead end. So now we go to the instruction register, and we analyze and go like, well, it's going to the D port of the instruction register. It is meaningful only if the instruction register is enabled so that it is going to update on the next rising edge of the clock, right? So now we look at the enable pin, and the enable pin is indeed a 1, which means on the next rising edge of the clock, the instruction register is going to use the data coming out of RAM to update its own content. So we have found the consumer of the data coming out of the RAM. Alright, so I'm just reading the text channel here. Does the reset button underneath the RAM reset only the RAM or the entire processor? Okay, that's kind of it's a relevant question, but it is also kind of distracting from the main discussion. But if you look at this wire, it only goes into the clear of the RAM. So this one only clears the RAM. It doesn't do anything else to the processor. All right. So now that we have answered the question, so the fetch operation. So let me go back to the tablet so that you guys can see what note you're supposed to be taking. Okay. So the fetch operation or the fetch cycle. Okay, most people call this the fetch cycle. In text toy processor, okay, because other architectures can design this slightly differently, so it may not work exactly the same way. So in text architecture, this occurs when the microcode pointer is 0x000. I use 0x here because I want to emphasize that we are dealing with hexadecimal. And we also want to specify this is it occurs at a rising edge. Okay, and then the operation itself is the instruction register. I'm going to use IR as the abbreviation of the instruction register. Is going to be updated by whatever the PC is pointing to. So if I want to use C notation to describe what the fetch cycle is actually doing, this is what it's doing. Okay, it is saying the instruction register is getting the content in RAM where the PC, the program counter, is pointing to. All right. So I'm certainly hoping that everybody in this class feel comfortable with pointers because we're going to use it a lot. And this is also why CISP360 is a very, very important prerequisite to this class. Yes, I know. But we are not going to use structures, not yet. So we are just using pointers and go into a particular location in RAM and go like, okay, we'll grab that content at that location and stash it somewhere. All right. So getting back to the processor. So now we want to do a control T. Control T is a single clock update, a single edge. Okay, it gives you a single edge. So the clock is going to go from dark green to green, which means it's going to go from 0 to 1. So I'm going to type control T right now on the keyboard. Control T. Ah, okay, we can see that. We can see the instruction register is now 7-8. Woohoo! Okay. What is going to happen now? It's going to be a falling edge, right? So all registers do not update on the falling edge with one single exception, which is the microcode pointer. The microcode pointer, if you look at the trigger, is on the falling edge. That's the only one that is going to update on a falling edge. There's a good reason for this, but I'm not going to explain it yet at this point. Okay, so the microcode pointer is going to update when I control T again. Then the next question is, how is the microcode pointer going to update, right? How is it going to update itself? So now we need to analyze kind of this portion of the circuit again. Okay, well, this is the first time actually. This is the first time we actually analyze this portion of the circuit. All right. So the first thing we know is the enable of the microcode pointer connects to a constant of 1, so the microcode pointer is always on, is always going to be updated on a falling edge. Okay, so every single falling edge is going to update the microcode pointer. But how is it going to be updated, right? So we have to track down the D port, okay, and see what is coming in. Unfortunately, it is coming in through a multiplexer, which means now we need to look at the select pin of the multiplexer so that we know which input is connected to the D port of the microcode pointer. And it is a 1, right? And this 1 is also coming from the 1080007 in ROM, because that is one of the wires coming out of the D port of ROM. So everything that we have explained up to this point, how RAM is configured, how the program counter is configured, everything that we have explained up to this point is because of the content at location 000 in ROM. Okay, that is super important. Okay. All right, so we know it's coming from input 1 because the select is specifying 1. So now we track down input 1 of the multiplexer, and it's coming from an adder, right? So this is an adder, and this adder is adding whatever the microcode pointer has to 0, but also to 1, because carry in which is kind of equivalent to our K0, is one of the things being added. So there are actually 3 things being added by adder. It is the carry in, the top input pin, and then the bottom input pin. They are all added together to become the output. And because the bottom input pin is 00, is a constant of 0, so that means we're just adding 1 to whatever the microcode pointer now has, so that becomes the output, which then goes around through the multiplexer, going back into the D port of the microcode pointer. The microcode pointer currently has a content of 0, excuse me. So it has a content of 0. So after we add 1 to 000, we have 001. So when I type Control T on the keyboard, we can expect the microcode pointer to increment from 000 to 001. So I'm typing Control T right now, and there we go. So this is just preparing for the next location, because you can see how the ROM is now addressing location 001 instead of 000. But 001 has a different content, so that means we are reconfiguring everything in the processor so that the next rising edge is going to do something. Okay, it's going to do something different from what it used to do before. So to understand what it's going to do, we're going to have to do the same thing again. Okay, so the first few times is going to be difficult, but you're going to have to do it. Okay, because if you avoid doing this, that means by the time we get to the exam, you won't know where the components are. Okay, not as not quickly enough to be able to answer the question. So you want to kind of practice this, when you're not in an exam, to find out, oh, RAM is over here. And in this case, RAM cell is a 0, which means we are not using RAM at all. Okay, so we can ignore that. So now we have to look at other things that are enabled, okay, and see which one we are using in this particular cycle. This is the ALU, and the ALU has its own enable pin, which is this one here. You can see how it is dark, right? It's a dark green, which means the ALU is not in use. So we don't have to bother with, okay, what is going into the ALU and who is the output of the ALU and so on. Okay, no need to worry about that. The flags register is also not enabled, so we don't have to worry about how it is going to be updated. And then we look at basically everything that has an EN or SEL. We kind of want to pay attention. Okay, so this is a 0, and this is also a 0. So that means none of the registers inside the register bank is getting updated. Okay, so we don't have to ask how is it updated. And then we just look around. So once again, when you are preparing for the exam, and I'm not even going to be not even for preparing for the exam, okay, after this class, okay, you might want to just kind of make a picture or a PDF or PNG of the processor, and then just highlight the things that are important to investigate so that you can understand what the processor is going to do. The PC stands for program counter, exactly. Yep. Okay, so now, and the thing is, don't start with the multiplexers or the demultiplexers, okay? Because the multiplexers and demultiplexers, they're switches, okay? You only have to investigate those things when you already know that one end of the multiplexer or demultiplexer is in use, okay? Because if nothing is in use, who cares about how the tracks are switched, okay? So there are two registers here. One is the instruction register, which is in dark, which is not enabled, and then we have the program counter, which is enabled. Okay, because PCEN is a 1, so the program counter is enabled for an update. It's not updating yet because it updates on the rising edge. So when I type Control T again, then the program counter is going to be updated. So once we know that the register is going to be updated, the next natural question is, how is it going to be updated? Okay, that's always kind of the case. Okay, so you can kind of follow the reasoning here. Okay, if I know something is updated, then the next question is, how is it updated? So to understand how the program counter is going to be updated, we have to track the D port, which is coming from a multiplexer. This multiplexer has the select pin specifying a 0, which means we have to track down input 0. Input 0 is coming from something that looks like something that we have seen before, okay, with a slight difference. So we can see this is also an adder. We are adding 1, so the program counter is getting updated by something plus 1. So the next question is, what plus 1? So we follow the top input pin, and then we see that, oh, it's coming from the program counter itself. So basically, the program counter is auto-incrementing with this particular cycle. So we are basically just saying, hey, program counter, auto-increment, add 1 to yourself. So the next question is, why are we doing this? Okay, the reason why we're updating the program counter and make it kind of auto-increment is because the content at the location 00 is already used. Okay, we have already stashed the content at location 00 into the instruction register. So it's time to move on to the next instruction, the next location. All right. So it's really kind of important to understand the rationale of why each thing is used the way that it is. So it's not really just memorizing, because there's no need to memorize. I mean, you can use Logisim while you're in the exam, so there's no need to memorize. But you do have to understand the rationale and how things are connected conceptually. How things are connected in the circuit, you can see it, right? I mean, this is just a map. But why are they connected the way they are connected? That is something that you do have to kind of connect in your mind. Yeah, sort of. One is one deals with RAM and the other one deals with ROM. So that's, they're a little bit different in that respect. But they are similar. Yes, but they are similar. So now I'm going to type Control T on the keyboard, and we can expect the program counter to increment to 1. Woohoo! That's it, right? So now we're going to have a falling edge. So once again, with the falling edge, you can forget about everything else, because the only thing that is sensitive to a falling edge is the microcode pointer. So now we look at the microcode pointer and ask, how is it going to be updated? Is it going to be auto-incremented again? Well, no, right? Because when you track down the D port and you go through the multiplexer now says, let's use input 0 instead of input 1. So it's not auto-incrementing this time. So input 0 comes from a splitter, which in this case is kind of like a merger, because we are reading the merged end, so it's kind of like a merger. So the merger is kind of interesting, because if you track down this part here, it's coming from the instruction register. Okay, so the 7-8 is here because it is just coming from the instruction register. But the top part is coming from a constant of 0. So now we have to kind of, let me take a closer look so that it is clear how the splitter works. Okay, so we can see, for this particular splitter, bit 4 to bit 11, they're coming from the instruction tunnel. The instruction tunnel is really just a simple tunnel, so that I don't have to draw a wire from here down to here, which is really not an issue, but it's going to cross a few wires, so it's just going to be ugly. That's the only reason why I use a tunnel. So for all practical purposes, this is the output of the instruction register. And then the bottom 4 bits, okay, the least significant 4 bits, they're all zeros. So that means by the time everything is merged, okay, when we look at this wire, instead of 7-8 in hexadecimal, we get 780 in hexadecimal. So it's really kind of the same thing as whatever the instruction register has, and then left shift 4 bits. Okay. So that is going to be that will be used to update the microcode pointer, which basically means the ROM is going to jump from location 001 to 780 in the next transition, in the next clock transition. This is called the decode cycle. Okay, this is called the decode cycle. So I'm gonna go back to my tablet again to help you write down some notes. So next we have the decode cycle. So for the fetch cycle, you can sort of include PC++ on the next rising edge as part of the fetch cycle. So whether PC++ is a part of the fetch cycle or not is kind of fuzzy, okay? Because the purpose of the fetch cycle is really just to grab the next opcode. PC++, is handy so that we would have the program counter pointing to the next location already by the time we get to the instruction itself. So that's kind of optional. Okay, the decode cycle, on the other hand, is the microcode pointer being in hexadecimal 001, and this is going to be on the falling edge. And what it's going to do is to say the microcode pointer is getting whatever, oops, not the reference, is whatever the instruction register has, left shift by 4 bits. That is the decode cycle. Now the decode cycle Why is the microcode pointer 12 bits? Because originally I thought I would need a lot of slices. I would need a lot of steps per opcode, but that turned out not to be the case. So I just ended up wasting a lot of space in the ROM, and also making the microcode pointer unnecessarily wide. That's why. All right. So now we have two cycles explained. We have the fetch, we have the decode, and then when we switch back to the processor and type a Control T, and you might want to focus on the ROM component here. Control T, and voila! I mean, right away we jump to location 780, which has obviously its own content. So what do we do now? We have to do exactly what we just did before. Okay, we have to track down, where things are, who is enabled, who is not enabled, blah blah blah. Okay, so now we have to track down things, and once again, you might want to specify your own order of what you want to check. I personally always check RAM first, and then I check the registers and so on. But you might want to, you can decide how you want to do this, okay? But whatever you do, make a list, okay, so that you don't miss something. So I always check RAM first, and then RAM in this case is selected. It is active, so that means the next natural question is, am I reading or writing? We are reading because LD is a 1. So knowing that we are reading from RAM, then the next question is, where are we reading from? Okay, that's going to be the next question. And I think something is not right here. Oh, okay, never mind. It is actually right. So the next question is, where are we reading from, and who is getting updated from this particular read operation? Sort of. Okay, I'm just going to be answering Jonathan's question here. So you can look at the content of ROM as subroutines, and then each opcode is kind of like the invocation of a subroutine. So each opcode is kind of like a macro. It specifies a macro, and then the macro is expanded into smaller steps of operation specified by the ROM. So that's kind of one way to look at it, and that's why the content in ROM are called microcode, because it is it's underneath the code, underneath the opcode. What we see in RAM are the opcode, but what we see in ROM are the microcode for the opcode. In other words, it would take several steps of the microcode usually to implement one opcode that we specify in RAM. Yep, sure, absolutely. Okay, so now we ask those questions, right? We ask the question, who is specifying the address port, and who is taking the output from the data port. One thing at a time. I always track down the address port first. Okay, so how you want to do things is up to you, but once again, make a list, okay, so that you don't miss asking one of those questions. So I just track down the A port, okay, and click on it. Since we're going to use Logisim during the exam, you can just click on the wire and find out where it connects to, right? So once again, we find that it connects to the same multiplexer. That part is going to be constant, right? We're not changing the actual wiring, when we run the processor. But this time, address mux is specifying a 0, which means we now track down input 0. And this is an easy one, right? Because there's only one place it's coming from, which is the demultiplexer here. This demultiplexer, so at this point we want to make sure that this output of the demultiplexer is in fact the one being selected. But that is confirmed by looking at this wire, because this wire goes to the select pin of the demultiplexer. So indeed we are choosing output 0 as the output of this demultiplexer. This particular demultiplexer, unlike this one over here, does not have its own enable pin, which means it is always enabled. So now we look at this wire and go like, it's coming out of out 1 of the register bank. Okay, what does that mean? So now we look into the register bank. Okay, so we use right click and then view register bank, and out one is reg out one. So now we look at this and go like, all right, so where is this one going to? Okay, what is connected to this particular output of the multiplexer? This multiplexer has a select of 0, 0. It needs 2 bits this time because it has 4 inputs, right? So out of the 4 inputs, we are choosing input 0 because 0, 0 in base 2 specifies just 0. So now we know, okay, so now we track down this particular node, and it comes from register A. So the output of register A is what is driving port A of RAM. Okay, that's good so far, right? I'm just going to check the text channel, no new questions. And now we go back to the main circuit because the next question is, all right, what about the data port of RAM? Who is updated by this particular pin, by the output of RAM? So now we track down all of these, connection points. We look at this one and go like, okay, this demultiplexer is turned off because it has its own enable pin and it's off, so we don't have to worry about it. We look at this multiplexer, and we can see this multiplexer is selecting input 0, and since the highlighted wire is connected to input 1, that's also a dead end. And then we check the usual suspects, right? Which is the instruction register. The instruction register is not enabled, so that means we don't need to worry about the instruction register. And there's only one more place that it can go, right? Which is this particular multiplexer. So when we look at this multiplexer, which has its own enable, which is a 1, so that means whatever is presented to the selected input is in fact going to the output of this multiplexer. So that means we kind of need to track it down now. So we can see that it's going into the register bank, and we have to be careful of which port it is connected to when we look at the register bank. So we can see it's connected to the in port of the register bank, and then in enable is also a 1. In other words, in general, when you see an EN, something EN being a 1, that means that something is active and you need to track down something. Okay, so now we go back into the register bank that we just looked at a little bit earlier, and then we've tried to find out, okay, what is enabled. Now when you're in this view and you go like, but I have no idea which port connects to which input port and output port of this thing. The trick to do this is to look at the appearance of the register bank. So you can, I'm not sure whether you can do that or not. I think you can. There we go. So you can switch between the actual circuit and also what it looks like, as quote-unquote a package on the outside. So this package view is kind of like the prototype of a function or a subroutine. You specify the return type, you specify the name of the function, you specify the parameters and the type of the parameters. That is the prototype of a function. This, on the other hand, is the implementation or the definition of the subroutine. So that's kind of the difference between these two views. You're looking at the prototype, you're looking at the implementation. Now, from the prototype, you can always kind of click on a pin, and it will show you in a picture-in-picture where that thing is located in the actual definition of the circuit. So this is how you can quickly locate, which pin is which pin, when you can only see the outside interface in the main circuit, and this is the inside circuit. So by switching between these two and clicking on a pin, that allows you to kind of make the connection of which pin is which one in the actual implementation of the circuit. All right, so getting back to here. All right, so this one is INEN, okay, input enable. So all that does is to enable this decoder. And then somebody's going to say, but Tech, I know you have not talked about what a decoder is. You are correct. We have not talked about what a decoder is because it is very simple to explain. A decoder is like a demultiplexer with only one difference. The input is a constant of 1. So you can just imagine that a decoder is like a demultiplexer where the input is a constant of 1. That's it, okay? um, all right, so the decoder is active, which means one of its output is going to be connected to the input constant of 1, and that is controlled, or it's determined by the gray dot again, which is the select pin. The select pin specifies 1 0, so that's why 1 0 in binary is 2 in decimal and also in hexadecimal, and that's why you can see output 2 is a 1, because this is connected to the implicit input of 1 of the decoder. And where that connects to is the enable of register C. So that means register C is now enabled to be updated. How is it going to be updated? Well, whatever is at the location the register A is pointing to. Now, obviously, at this point, you go like, but Tack, this is going to be super boring because register A is 0, 0, register C is 0, 0, and the content at location 0, 0 is 7, 8. So is that going to be how register C is going to be updated? The answer is yes. Okay, on the next rising edge, register C becomes 7, 8. Okay, and that is because register A has a default value of 0, 0. When we first initialize, when we first start Logisim, the default state of all the registers were zeros. Now, in case you feel, but Tack, this is really boring, I'd like something that is a little bit more fun and a little bit more interesting. Fine, we can do it that way. So this is the thing you can do, when you're single stepping through and you're just testing what an instruction does. Okay, so we can now play with this, right? So we can go to a kind of sort of random location, which is this one. That's location 08090A. Okay, so this is location 0A. I will just put in some random content here. Okay, we'll put in like 5C here. And let's just see. Let me retype it. 5C. There we go. So we'll put in the new content of 5C. So I just injected, okay, using Logisim, I just injected content into one of the locations. And then we can go back into the register bank, okay, because right now the processor has stopped executing. So we can do all of these magical changes. So I can now change register A to code to that, to point to that location, which is 0A, right? And you can see how the input pin has changed automatically. So it's already changed because everything is still running. I mean, the processor, all of the components are still quote unquote running, except they're not clocking. Okay, they're powered up, but they're not clocking. So that's why the changes are instantaneous. And on the next rising edge, now we can expect register C to update to a new content of 5C. Okay, so which is what I'm going to do now. So Control T, right there. And we can see how register C is now updated to 5C. So when we go back to the main circuit, this is called the execute cycle. Okay, so the execute cycle, has to do with when we get to the ROM location that corresponds to the opcode, and we start to go through those locations. That collectively is called the execute cycle of instructions. All right, so what's going to happen next? I have to look at the time because I really want to be able to finish this entire instruction. Label, I don't really need to talk about it because the lab actually has instructions to tell you what labels are and what to do with those things. The ALU stands for the arithmetic and logic unit. That's how we do all the calculations like addition, subtraction, comparison, right shift, and so on. Alright, so what we'll do now is to go back to the ROM because the next edge is a falling edge, and only one thing is sensitive to a falling edge, which is the microcode pointer, right? So we check out the microcode pointer. The clock is currently a 1, which means the next Control T is going to make a falling edge. So now we want to know how the microcode pointer is going to be updated. So we track down this wire going to port D coming from a multiplexer. The multiplexer selects input 1, so we track down this wire. This wire is coming out of the incrementing mechanism. And in this case, we don't have to worry about adding a 0 because this is a constant of 1. So we are always adding 1 when it comes to this particular adder. So that means the microcode pointer on the next falling edge should become 781. Okay? But it would not appear so. So when I do a Control T, you will see that, but Tech, you said microcode pointer is going to be going to 781, but that's not what we are seeing. Why? Okay, I'm just predicting the future, just predicting the next 20 seconds or so. All right, so we'll give it a try, right? Control T, you go like, oh, Tech, you said the microcode pointer is going to be going to location 781, but it's not. That's not what it's doing. Deja vu, right? I mean, I already predicted that this is going to be the question that I'll be getting. And I can do this because I am the doctor. Nope. It actually went to location 781. It actually went to location 781, and whatever is at location 781 was causing the microcode pointer to automatically switch to 000 right away so fast that we could not see it. Nope, it's not all zeros. Okay, so let's check this out. Okay, so whenever we see something that we cannot explain, what are we going to do? Or what do you think Tech is going to do when he sees something that he doesn't know?
Okay.
It's magic. Take a nap, burn it, cry. No, I'm going to ban it. Whatever I don't understand, I will ban it. Because then I don't have to worry about it. Nobody's going to talk about this again, ever, because I don't understand it. So I don't want you guys to talk about it or mention it ever again. Of course, we're going to investigate it. Okay, we're going to find out why that is the case. All right, and this is, I know it's going to burn up some minutes in the class time, but this is really important. Okay, the mentality is really important because this is what debugging is about, right? When your program doesn't work the way it's supposed to do, it's a mystery. Okay, and a lot of people get frustrated because they want the program to work and they think the program should work. So that's a lot of judging. Okay, in terms of MBTI, the Myers-Briggs type indicator, people with a strong J as the last letter, they tend to think that way. Okay, there's a lot of judging. Okay. So there's a lot of should, it ought to, there's a whole lot of expectation stuff, right? But when the program doesn't work, it doesn't work. I mean, that's just factual, that it's not working the way you think the program should be working, should be doing. So what do? Frustration is not going to help. So instead, just try to step by step figure out why is it doing whatever it is actually doing. Okay, it might take a few steps. You might need to use the debugger. But the thing is, there has to be an explanation. Okay, we just have to find it. Yes, the needle is in the haystack in this case. Okay, we are not, and the haystack is finite also. For those people who are also taking 440, you know what I'm talking about. Alright, so we're going to go into the ROM content. Okay, it's really big as a window because I have a large monitor, so it decides to use a really, really big window. So I'm going to have to resize it a little bit first before I put it back into view. There we go. Alright. So we want to we want to go to location 781. So we need to scroll. That was one of the popular questions on Tuesday. How do we get to that location AA0? Scroll. Alright, so 780 is here, and we can see 781 is 2 followed by how many zeros? 6 of them, right? 1, 2, 3, 4, 5, 6. Yep, 2 followed by 6 zeros in hexadecimal. Why would that cause such a mystery? Why didn't we see that the ROM is staying at location 781 and the content at that location is 2 followed by 6 0? What is so special about this bit? Now, the first thing we notice is this word here. I call this a word because it is the content of one memory location in ROM. Okay, so that's a generic word, generic way to use the phrase word. Is basically the content of one location. And we know only one bit is turned on because all of these zeros cannot be possibly contributing to a bit of 1, right? So we know all of those are going to be zeros. So we know we are accounting for 24 zeros right there because we have 6 hexadecimal digits of 0 and each one is accounting for 4 bits, right? So now we only have the 2 left. But 2 itself is a power of 2, so that means the 2 in hexadecimal is only specifying one bit being a 1. So now the question is, which one? So now we go back to the circuit here, and then we look at the output of D, and 2 zeros. Okay, so this is how we figure this out. Okay, so let me go back to the tablet so I can show you how we figure out the bit representation when we have the hexadecimal representation. So let's see. Let's start a new page. There we go. All right. So we have 2 followed by 6 zeros, right? Each one of these is accounting for 4 bits. So that means from bit 0 to bit 23, they're all zeros. Somebody's going to say, but Tech, your math is wrong. Okay, 4 times 6 is 24, not 23. I know that. It's 23 here because we count from 0. Okay, because we refer to the least significant bit as bit 0. So the most significant bit of these 6 hexadecimal digits is known as bit 23. Okay, what about this 2? So this 2 is a 0, 0, 1, 0. Since this is corresponding to bit 23, bit 23 is the most significant bit of this hexadecimal 0. So that means this is bit 24 and this is bit 25. This is how we count bits. So now, okay, let me just read the text channel. Is it because it's 1 more than the maximum number of bits that can be held within 7 digits? Not really quite sure how to interpret that question. But we know that bit 25 is a 1. So we know somehow bit 25 being a 1 is causing some strange behavior. So we'll track down where it's going. It doesn't go too far, right? I mean, it just goes into this OR gate. But remember, this is an OR gate, which means if at least one input is a 1, the output is going to be a 1. So that means at location 781, this line is also going to be a 1. Where is that going? Can someone explain to me what is this 0 thing doing in a register? Exactly. It's reset, clear, 0 out, whatever you want to call that. But it's going to change the content of the register to become all zeros again. That is why we are now back to location 0, 0, 0, because we have just executed one instruction. We are now ready for the next one. This is also why the auto increment of the PC was important, because now we know where we are reading from, right? Because if you track down the content of the program counter, okay, we can see it here. It is already at location 0, 1. So we are ready to go to location 0, 1 in RAM, fetch it, put it into the instruction register, and then we decode it, and then we go to where do we go to in the ROM memory when the opcode is 0, 1? Which address do we go to in ROM? Okay, this is a quick quiz to see if you guys have been paying attention. We know the opcode is 0, 1. Where in ROM are we going to go to to quote unquote execute that instruction. And we got, nope, it's not register B. It has nothing to do with register B whatsoever, because the question was, which location in ROM are we going to go to in order to do the execute cycle for an opcode of 0, 1. Grant is correct. It is location 0, 1, 0. It really is just the opcode with one extra 0 on the right hand side. But remember, these are hexadecimal digits. Okay, these are hexadecimal digits. Yep, because of the bit shift. Well, what is equivalent to a bit shift? Yes. Cool. Oh, but that's the halt instruction. The halt instruction has an opcode of 0, 1. Don't you guys want to find out why the halt instruction is halting? I want to find out. Sure. Yeah, let's do that. So this time I'm not going to use the next 1 hour and 15 minutes to go through the whole cycle again. So I'm going to cycle through the first few ones here really quickly. The first one is the fetch cycle, which means the instruction register is going to get 0, 1 this time. So there we go. And then the falling edge is going to increment the microcode pointer to the next location. And this particular event has no it doesn't have a name. Okay, it's just not very important. So there we go. And then the next rising edge is going to update the program counter. It's going to auto increment to location 0, 2 to quote unquote prepare for the next opcode. I put it in double quotes because guess what? We are not going to go to location 0, 2 at all. So Control T, PC becomes 0, 2, and now we have a falling edge again. This is the decode cycle. The decode cycle is going to copy whatever the instruction register has to the microcode pointer with a shifting in after we shift in like 4 zeros on the right hand side. So it is so for people who think, but we are already there. No, we are not there yet, because this is 0, 0, 1. It is going to become 0, 1, 0. Okay, so Control T becomes 0, 0, 1, 0, and the first thing we find at that location is like, they're all zeros. What is that going to do, right? Well, we'll find out. Okay, we have another 3 minutes to find out, why the halt instruction is halting. So the first thing we want to know is what is active, what is turned on, in this particular cycle. Well, quite obviously nothing is, right? Because I already said if something is to become active, somewhere there has to be a 1 to an EN or SEL. Okay, RAM is turned off, right? So this is a good exercise to kind of go through things, to double check what is active and what is not. The ALU has an enable of 0. The register bank has an input enable of 0. Let's see, the program counter has the program counter enable being a 0. The instruction register has the enable being a 0. The flags register has the input being a 0. So basically everything is turned off. So if everything is turned off, that means the rising edge is not going to do a single thing, right? Okay, fine. Control T. Now we have a falling edge. Then someone is going to say, but the falling edge is going to do something, right? It's got to be doing something with the falling edge. Well, it does do something per se, but it's also not going to be very exciting either. Okay, so let's find out what this falling edge is going to do. I mean, it doesn't really take a whole lot of time to find out, right? Because it's the same analysis. We have done this already. And for those of you who think, Tech, this is really boring, I'm bored. Well, my response is, congratulations. I think, being bored at this point is good, because if you already understand what is going on and you know how to track things down by yourself already, and you don't need me to explain it to you, good for you. Okay. Now, on the other hand, if you say I can use a few more guided, instructions, that's fine too. So we're going to track down how the microcode pointer is going to update on this falling edge. Track this down, coming from a multiplexer. The multiplexer is selecting input 0, so it's coming from, guess what? The instruction register again. And then somebody's going to say, but Tech, the instruction register has 0, 1 in it, right? And the microcode pointer is already 0, 1, 0, so nothing is going to do. So the microcode pointer is really not going to change. Okay, even though this really is an update operation, the new value of the microcode pointer is whatever it already has, which is 0, 1, 0. This is why it is stuck. Okay, this is why this is called a halt instruction, because once you reach a halt instruction, the program is not going to go any further. And that's why it is special. And this is also why there's an output pin called a halt pin, just to indicate have we reached a point in the program that it is going to stop, that it cannot possibly proceed any further. And that is why the halt pin is really useful. When we get to the command line way of tracing a program, this pin, because of the way it is named, actually has significance, because it tells the simulator when it can exit, and not to collect any more data in the trace. So that's another reason why we have a halt pin, output pin. But for the time being, you can basically just look at this pin and go like, okay, if I just keep Control T, or if I have the program to run by itself, when I observe a 1 with this halt pin, that means we are done. We can stop, going through any further, transitions. All right, so I think we are running out of time in terms of the lecture. And it's perfectly okay. I did not actually have to go through the other 2 instructions, because you can now do that. Okay, because you basically have to just to do the same thing that I did in the past 80 minutes. Okay, is really just to track down everything in the processor. And this is why I want to use this processor to teach this class, is because it is completely open. There's nothing mysterious going on, and everything is out in the open. You can just, once when you're not having a transition, the whole thing is static, which means you can use the poking tool, you can examine the registers, you can examine every single node, find out, who has what, and what is connected to what else, using the multiplexers and the demultiplexers, before you do the transition. So you can kind of predict what is going to happen next, and you can use Logisim to confirm what you already understand, and not so much to have Logisim to tell you what it is going to do. No, the access code has not been given yet. So the access code is LDI. There we go. There we go. So I'm going to pin this one. There we go. So the access code is LDI. In this particular lab, I believe it also talks about labels, but the instruction or the description of label is part of the lab also. So the lab is somewhat self-explanatory, but if you do have questions, we have the next 3 hours or so for me to answer questions. So the lab does end at 9:50 p.m. Okay, so you probably want to kind of get started after you get a few bites, and then come back. All right. So next question is RISC-V. RISC-V. Huh. Okay, I'm not familiar with RISC-V. Okay, we'll take a look at. Okay, so it looks like it is similar, but an open source version of something like ARM. Would that be a kind of like what it is about? Yeah, so it's kind of like an open sourced ARM, where the architecture is open, which means people can incorporate this processor design without having to pay royalty or have to pay for the copyright to use it. That's kind of interesting. But I don't want to use anything complex, because the nice thing about the text toy processor is everything is graphical. I mean, you can just kind of follow the diagram, poke at a wire, poke at a node, and figure out, what is going where and how it is all happening. That's cool. I'm for it text toy processor is not practical whatsoever, but it does make things easy to follow. It's kind of like the same thing um, like the engine model thing, except this one is truly functional. If somebody were to burn this processor into silicon, it can actually do stuff, okay? Just not very practical stuff. So it's kind of like a tiny little 8-cylinder engine they can hold on your palm, but it actually goes through all the cycles. It actually turns. You can you can make a tiny little gas tank, and it will just it will run, but doesn't do much other than that. But by the time we get to the end of this semester, depending on how quickly we can go through the topics, we'll definitely get to the recursive implementation of Fibonacci for sure. Okay, if we have enough time, okay, that's a kind of big if here. If we have enough time, I can even show you guys, how to write a recursive algorithm to traverse a binary search tree. And the whole thing is going to be implemented in TTP instructions, and the whole thing is going to fit in 256 bytes of RAM. It's going to be cool. It's going to be kind of fun, but I don't know whether we will have the time to do that or not. And oh yeah, by the way, we can also do Hanoi's Tower. The recursive version of Hanoi's Tower can also be coded. There's enough instructions and there's enough stack space to do it. Yeah, everything fit into like 256 bytes. Oh yeah, I mean, of course, the first question the interviewer is going to say, "Why would you do that?" Because it's a challenge. Because I like challenges. All right. So I'm gonna go away for maybe about 10 minutes, and then I'll come back and answer questions. Cool. Alrighty. So you guys can kind of chat along, and I'm gonna kind of do a bookmark here so that I remember where I left off. So I'll be back in about 10 minutes, after I turn